going to be working the problems from the optimization section 4.5. Number 1 says, consider the following problem. Find two numbers whose sum is 23 and whose product is a maximum. So we want to find two numbers, x and y, whose sum is 23 and whose product is a maximum. Product is a maximum. So their product, x times y, is a maximum. All right, so what we want is the maximum product so we want a product function but we already have the product function. The product is, well, I say we have the product equation. The product is just x times y. I'm going to call it p. We want to know when this is the biggest possible. But right now, this equation, p depends on two variables. So I want to get rid of one of these variables. We also have a constraint. The constraint equation is already given to us. These numbers can't be anything. They have to add up to be 23. So I can solve this for x or y. I'm going to solve it for y. If I solve this for y, I get y is equal to 23 minus x. And so now what I can do is I can come over here and I can write the product is equal to x times 23 minus x, replacing y with that. And now I can notice that p is a function of x. So I have a product function here. And as far as a domain, really there was no restriction on what x could be. I can let x be any number. It doesn't matter, even if x is bigger than 23, let's say 24. 23 minus 24, that would give you -1. It doesn't say that these have to be positive numbers. So I have no restriction on x at all. So x can be between -infinity and infinity. That's my domain. And that means when I do this, I cannot use the closed interval method. I'm going to distribute the x through here. And so here's a nice polynomial function. I want to find its local maximums and minimums. So I take its derivative. And I get 23 minus 2x. And now I'm going to set that equal to 0. And I get 23 minus 2x equals 0, which means x is 23 halves. All right, so I also look at when the derivative is undefined or doesn't exist. This doesn't happen because it's a nice polynomial. So now I just take my 23 over 2, I put it on a number line. I just want to confirm that this is going to give me a maximum. So I pick a test point over here, let's say 0. I pick a test point over here, let's say, I don't know, 100. And I plug these into the derivative. So if I plug in 0 into here, I get a positive number. So that means my original p function is going up here. If I plug in 100, I get a negative number, which means my p function is going down, which means at 23 over 2, I get a maximum. And that's the only maximum possible because my function would have to go back up and back down again if I were going to have another maximum. Hold on just a second. Okay, and now, now that I know what x is, that gives me a maximum. So I have a local max at x equals 23 halves. What I'm going to do now is figure out what y is, and here's y. Y is this, so that means y would be 23 minus 23 halves. So I get a common denominator and multiply by 2 on top, so I get 46 halves minus 23 halves. So I get 23 halves again. So the two numbers that I would need are x is equal to 23 halves and y is equal to 23 halves. And their product is going to be 23 squared over 4, whatever that number is. And that's the biggest possible product I could ever get by multiplying two numbers that add up to be 23. All right. Did I turn that back on? Yeah. All right. Okay.
Thank you.
All right, no problem. All right, sorry about that delay. Let's see here, number 4. Why in the world? All right, number 4. The sum of two positive integers is 16. So you have two integers that add up to be 16, but I'm going to put here x and y are positive. What is the smallest possible value of the sum of their squares? The sum of their squares is this. I'm going to call this just s, okay? So what we want is the sum of squares. We want this to be the smallest it can possibly be. So we've got to turn this into a function of one variable. So what I can do is I can come back over here to the constraint. I know that those two numbers added up together have to be 16, which means that y must equal 16 minus x. Then I come back over here and I replace my y. And when I do that, I now write s as a function of x. This is 16 minus x squared. So there is my sum function, okay? And I want the domain. Now we do have domain restrictions here. The smallest that x could be would be 0, because it can't be negative. And if I let x be 0, then y is 16, that's fine. The biggest x can be would be 16, because if I go over 16 at all, then 16 minus something bigger than 16, that's going to be a negative number, which would mean y is negative, but they both have to be positive. So the smallest y could be was 0, and the way that's going to happen is x is 16. So I have a continuous function on a closed interval. I can use the closed interval method here. I'm going to go ahead and take the derivative of this now. This is 2x plus, this is chain rule, so 2 pops out, 16 minus x to the first power times derivative of what's inside, which is negative 1. So this is really just 2x. I'm going to put this negative 1 on this 2 and distribute it through. So negative 32 and then minus 2x, but then the negative is going to make it plus 2x. So we get 4x minus 32. That's our derivative. And we're going to set that derivative equal to 0. And we get 4x minus 32 is 0. So x is equal to 8. And there's nowhere where the derivative doesn't exist because it's nice. So x equals 8 is a critical number. So what I'm going to do now is I'm going to plug in, because this is closed interval method, I'm going to find s of 0, s of 16, that's the endpoints, and s of 8. And when I plug in 0 into the original function, let's see what I get. 0 here and 0 here. So if I do 0 there and 0 there, I'm going to get 16 squared. If I do 16 in here, 16 squared, and then 16 minus 16 is 0, I get 16 squared again. And if I plug in 8, let's see what I get. I get 8 squared plus 16 minus 8 squared. 8 squared is 64 plus 16 minus 8 is 8, so 8 squared again is 64. That's 128. So I get 128 there. 16 squared and 16 squared, those are both bigger than 128. So this is the minimum. So I'm going to get a minimum sum of the squares if I let x be 8. Okay, so if x is 8, the sum of the squares is going to be 128. So x must be 8, and of course that means that y must be also 8. And that means that the sum of the squares will be 128. And that's it for number 4. Whoa. Sorry, I'm just gonna check this. Oh, no. All right, moving on to number 7. Number 7 I did in class. So that is, you have a rectangle with a perimeter of 100, find the maximum area. So just refer to the lecture video for number 7. Number 8, find the dimensions of a rectangle. Okay, find the dimensions of a rectangle with an area of 1,000 square meters, whose perimeter is the smallest. So we want a minimum perimeter, which means I'm going to need a perimeter function. This is a rectangle. So I have a rectangle, call that x, call that y, and therefore the perimeter of this is 2x plus 2y. That's our distance around it. And we want this to be the smallest it can possibly be. But we're constrained. Our constraint is that the area is 1,000. Area of that rectangle is x times y is 1,000. And I can solve this for x or y. I'm going to solve it for y, and I get 1,000 over x. So this is my constraint. This is my objective function. So my perimeter as a function of x is 2x plus 2 times y, but y is this, so 1,000 over x. And so I get my perimeter as a function of x equals 2x plus 2,000 over x. All right, now as far as the domain is concerned, well, I know within the constraint of the problem, I cannot have x be negative because it's the length of a side of a rectangle, and y can't be negative. So definitely x has to be positive, but it also cannot be 0, because if I let x be 0, this is undefined and I will have no area. I have to have an area of 1,000, so x cannot be 0, but it can be any positive number. So my domain is from 0 to infinity, because if I let x get bigger, right, this fraction is going to get smaller and y is going to get smaller. But I can let x be 1 billion, 1,000 over 1 billion. Well, that just means y is going to be really small. So the longer x gets, the smaller y gets, and I can always maintain an area of 1,000. If I let x be big, I just need to make y smaller and smaller and smaller. And I have no real limit of how small y can be other than 0. So I should be in business here. This is not closed interval method, so I'm going to have to work at this a little bit. So what I'll do now is I'll take the derivative of this. The derivative of p is 2. And then derivative of this, remember that's really like 2,000 times 1 over x. That's what that really looks like. The 2,000 comes for the ride. Derivative of 1 over x is negative 1 over x squared. So this can become negative 2,000 over x squared. I know I'm going to be setting this equal to 0, so I'm going to get a common denominator now. And now when I set it equal to 0, I just have to set the top to 0. And that's going to be x squared is 1,000, which means x is 100. So if x is 100, I have a critical number. Now, where is the derivative undefined? Where doesn't it exist? That's at x is 0. X is 0 is not even in the domain of the original function, but I'm just pointing out that I do have issues there. On a number line, I put my 100 here, and see, I would normally want to put 0 here, but you know, the function isn't even defined over there, so I don't need a test point over there. So here, pick something like 10. Here, let's pick 1,000. Let's plug those into the derivative, and what I'm hoping for is that it's going to go down then up. So if I plug in 10 into the derivative, let's do it right here. 2 minus 2,000 over 10 squared is 100, so 2,000 over 100, that's 20. 2 minus 20, that's a negative number. So my p function is going down over here, that's good. If I plug in 1,000 squared, 2,000 divided by that, that's going to be smaller than 1. So 2 minus that should be a positive number. I'm going through that fast because I assume you could plug these two numbers into that and figure it out. So it does look like we do have a local minimum, and in fact this is our only minimum because it goes down and up, never comes back down again. So that means that p has a minimum at 100. If x is 100, that means that y, if I plug into my constraint for y must also be 100. Wait a minute, 10? X is 100. Yeah, 10. Y is 10. Then this will give me minimum perimeter. Yeah, that's what I wanted. Is my basic math off the wall here? Did I forget? Oh, my goodness, Robert. Okay, no excuses for this. 100 times 100 is 10,000, not 1,000. This should just be square root of 1,000. Take the square root of both sides. All right, square root of 1,000, that's still in here. Square root of 1,000. 1,000 is still out here. So I messed up over here, my fault. So square root of 1,000, I can still pick these two numbers, it still works. But now if I want to know what x is square root of 1,000, and that means y is 1,000 over x, which is square root of 1,000. And if I rationalize this, I can multiply top and bottom by root 1,000. I get root 1,000 times 1,000 over root 1,000 times root 1,000. This is 1,000 right here, and that cancels with that, so you just get root 1,000 again. So it needs to be a square. So to get the minimum surface area, you make it a rectangle where it's square root of 1,000, square root of 1,000, and that'll give you your minimum surface area, and the area of that's still 1,000. Now, I said surface area, I meant perimeter. That'll give you the minimum perimeter. Now, what is the perimeter? I don't believe they ask for that. Find the dimensions. But if I wanted to know what the perimeter was, I could just plug in root 1,000 into here, right? I could do it right there. Yeah, let me do it. The perimeter, just so we know it, would be 2 root 1,000 plus 2 root 1,000. That would be my perimeter, which is 4 root 1,000. So if they had asked us what the actual minimum perimeter was, we would say it's 4 root 1,000. All right, sorry about that. Basic arithmetic. Not paying attention. Okay, let's see, number 9. Consider the following problem. A farmer with 700 feet of fence wants to enclose a rectangle and then divide it into 4 pens with fencing parallel on one side of the rectangle. So here's the deal. This farmer has 750 feet of fence. He wants to build a rectangular pen like this. Then he wants to divide it into 4 equal pens. So imagine cutting this into 4 equal pens. He's got to use fence for all these sides. The sides are parallel, that's what he was saying. These are parallel. So what is the largest possible total area of the 4 pens? So I want to find the maximum area total of all the pens. That's what I want. So I need an area function. I need an area function. Well, the area of this thing, I need to label some things here. Why don't we call the distance from here to here, why don't we call this x? And why don't we call the distance from here to here y? Then the area would be all of this, which is 4x's, times y. That's the area of the whole thing. So the area of the entire enclosure is 4xy. Now this area equation is not a function of a single variable yet. I have 2 variables in there. So what I need to do is somehow bring in the constraint. The constraint is that I only have 750 feet of fence. So let's talk about how much fence we're going to need. We're going to need whatever x is, we're going to need 1 of those, 2 of those, 3 of those, 4 of those, 5, 6, 7, 8 x's. So I know that my 750 has to be equal to 8 x's plus I also need this distance from here to 1, 2, 3, 4. I need 5 y's also to build this fence. And now what I can do is I can solve this for x or y, and I'm going to solve it for y. So let me do 750 minus 8x equals y, 5y. And let me divide by 5. Okay, so it goes in there 1. I seriously cannot do simple math. 120. 5 goes in there, 120, 50. No. Oh my gosh, Robert, what is wrong with you today? Yeah, that's right, okay. And then minus 8/5 x equals y. All right, is my microphone back on? My simple arithmetic is just, my brain is shut down. I think I'm ready for the break. 150. Damn, Robert. All right, so that's y. This is my constraint, and that allows me to come back over here, and I can rewrite the area as a function of x is 4x, and then here 150, take away 8/5 x. There we go. Let me distribute through here. So I have 4, okay, here we go again. 400, 200, okay, so 600x minus, when I multiply this times this, I get negative 32 over 5x squared. So that right there is my area function, and now I need to find its domain. So the smallest x could be would be 0. Of course, because x is the length of one of those pens. So the smallest x would be 0. And the biggest x could be, let me see if any of these are good. Oh, I know these are not good. The biggest x could be, we have to be careful here, we want to know basically what it would take to make y be 0. So in other words, what if I use all 750 feet of fence for these sides and left myself nothing for the y's? That means y would be 0. So if I let y be 0 here and solve for x, then move things around, 150 equals 8/5 x. 5 times 150 is 750. 750 equals 8x, and then divide by 8. So let me see what I get there. 93.75. That's the biggest it could be. All right, so we can use the closed interval method here. We're going to need to take the derivative. So let's take the derivative here of a. So a prime of x equals 600 minus, okay, 2 comes out here, so you get minus 64 over 5x. And I'm going to set this equal to 0. And I get 600 minus 64/5 x equals 0. Move things around, 600 equals 64/5 x, and I'm going to multiply both sides by 5 and then divide by 64. And that will give me 375 over 8 is x. That's as a fraction, but that as a decimal, 46.875 is x. All right, now let's go ahead and figure out what the maximum area will be by taking the critical number and taking the endpoints and plugging them into the original area function. So the original area function is right here. So I want a of 0. I want a of 93.75. And I want a of 46.875. So I'm going to trust that you could plug those in. I'm going to do that right now. I'm going into the original function because I'm using the closed interval method. Okay, give me a second here. I know if I plug in 0, I get 0, so I don't really need to worry about that. And if I plug in 93.75, I get 0, which is what I would expect. And then if I plug in 46.875, I get 14,062.5. All right, so this is obviously the maximum area I'm going to get. So this is it right here, and this is going to be in, this was feet, so this is going to be feet squared. That's your maximum area. It happens when you let x be 46.875. It doesn't ask you for what y is here, but you could go back to the constraint and you could find y. To do that, you use that constraint equation and replace this with 46.875. I'll go ahead and do that. 8 times. Should get 75 for y. So if y is 75 feet and x is 46.875, then you will have the maximum possible area. So back on our picture, y has to be 75, and x was this. This is 46.875, but the whole length would be 4 of them. I'm just getting this information just to have it. We don't need to do this. We've already answered the question right here. So if I take 46.875 and I multiply it times 4, 1, 2, 3, 4, that means this side right here would be 187.5 feet. 75 feet. So if I do that, 187.5, another side 187.5. So this side and this side together are 375 feet of fence. And then 75 5 times is 375. So 375 feet of fence for this, 375 feet of fence for that. That'll give you your 750 and give you the most area possible, which is 14,062.5 feet squared. All right, let's look at number 10. Consider the following problem. A box with an open top is to be constructed from a square piece of cardboard, 3 feet wide, a square piece of cardboard. So we have a box that's going to be constructed from a square piece of cardboard that's 3 feet wide, which means it's 3 feet tall because it's square. Okay, so a box is going to be constructed from this. The box is going to have an open top. We're going to cut out squares from each corner. We're going to bend up the sides. So we did this in class. The only thing is in this one, it's a square. It's not a rectangle. So we're going to fold up the sides and create this open top box out of it. So there's our open top box. The amount that we cut out from each side, remember we did in class, we called that X. So if that's X and that's X right here, then when we fold up the sides, this side right here will be the total distance from here to here, which is 3. But then we cut off the 2 X's, one on each side. So this is going to be 3 minus 2X. And this side right here is also 3 minus 2X. And this right here is X. It says find the largest possible volume. We kind of knew that already because we've done this problem. So we want the largest possible volume. So we want to find a volume function. Find the maximum volume. So that means I need to find a volume function. And the volume function is pretty straightforward here. The volume of that box is already a function of X. It is 3 minus 2X times 3 minus 2X times X. If you multiply that all out, you get 4x cubed minus 12x squared plus 9x. So that's what would happen if you actually multiply this all out. So this right here is our volume function. Now we need to look at some restrictions on x. Obviously the smallest x could be would be 0. And then the biggest x could be is if you went all the way, not across, but halfway, because you have to be able to come from both sides. So 1.5 feet. And this is a continuous function closed interval, so I'm going to take derivative of this. I get 12x squared minus 24x plus 9. I'm going to set that equal to 0, figure out where it's undefined. It's only equal to 0. We don't have to worry about the undefined. So if I take the derivative, set it equal to 0, so take that quadratic, set it equal to 0. I'm just going to tell you what the answers are. You get 1/2, and you get 3/2. So 0.5 and 1.5. 1.5 is one of the endpoints, so we don't even need to really consider that. But since this is closed interval method, I'm just going to be plugging these answers into the original volume function. So I want v of 0, v of 1.5, I want v of 0.5. And we know that if we plug in 0 into the volume function, I'm going to get 0. Check for yourself. If you plug in 1.5 into here, you should also get 0. And let me plug in 0.5 into that. Forget. I'm going to plug 0.5 into this right here. If this thing ever finishes doing, okay, 3. I get 2. So this is obviously the maximum. So I should cut out from this thing, this is 3 feet wide, I should cut out 1/2 foot, 0.5 from each side, 0.5 feet. And the question is asking us to, I think, find the largest volume. Largest volume is right here, 2. So it's 2 cubic feet, because it's a volume, it's cubic. And that is all. All right, doing okay here. Let's look at number 15. '15 is similar to something we did in class a little bit. Find the point on the line y equals 2x plus 3 that is closest to the origin. Origin is 0, 0. So if we have that line, which I can draw a rough graph of that line. Here's the origin here. This line has a y-intercept of 3, and then it goes up 2 over 1. So that line looks something like this. I want to find the point on this line, which I'll put up here in purple, although it'll be hard to see. Somewhere on this line is a point that is closest to the origin. So we did this in class. We know that the distance between 2 points is the square root of x2 minus x1 squared plus y2 minus y1. We're going to try and find the minimum of this. But we know something about these points. This point right here, which I could call my x1 and y1, that's 0, 0. And this point right here, since it lives on that line, it has as its coordinates x, and then the y is going to have to follow that formula, so 2x plus 3. So this is my x2, y2. This was my x1, y1. So I come back to this formula, my distance should be, let's see, x2 minus x1, so x2 minus x1, that's just x, and then squared. That's really x minus 0, but I didn't write it, but that's what it was. Plus y2, which is 2x plus 3, take away y1, so 0. So this is just 2x plus 3 squared. That's nice. So my distance is now a function of x, This is square root of, like I said, that was just x squared, and then plus 2x plus 3 squared. I want to find the minimum of this, right? The minimum of this function. The domain of this, if we look at this, our x value, right? Our x is the x coordinate of this purple point. And there really is no restriction. I can be anywhere on this line. So there is absolutely no restriction on the x. So domain of this is negative infinity to infinity. Now in class we discussed that to do this problem, to find the minimum of a square root function, hey, where's my, oh, there it is. To find the minimum of a square root function, what we do is we convert the problem into just looking at the minimum of the radicand of what's underneath. So I'm going to change this d, I'm going to call it r of x for the radicand. I'm really trying to find the minimum of this function. Whatever the minimum of this function is, will be the same as the minimum of that function. So same domain, let's go to town with this. I need to take the derivative. Wrong class. You take the derivative. And derivative of this is 2x. Chain rule here, 2x plus 3 times derivative of what's inside, which is 2. So this is 2x. Let's see, that's 4x, but then times 2, so plus 8x. And then here to here, that's 6, but then times 2 is 12. So we just get 10x plus 12. That's my derivative. If I set that equal to 0, I get x is equal to 12 over negative. No. Yeah. Whoa. Okay. X is equal to negative 12 over 10, which is negative 6/5. All right. Where's my derivative undefined? Well, it never is. So now what I'll do is I'll go to a number line. I'll put negative 6/5 here, 0 here, and let's say negative 10 here. I'm going to plug these into the derivative. And what I'm looking for is down then up. So if I plug in negative 10 here, obviously negative 10 times that plus that, that's negative. And then if I plug in 0, I'm going to get a positive 12, so it goes up. So my r function goes down then up. And that means this is where I have the smallest r. And wherever you have the smallest r, that means the inside of this is small, and that means the square root's going to be the smallest. So I have a minimum d, right? D has a minimum at x equals negative 6 over 5. All right, but then what's y? I need the point, right? I know what the x coordinate is, but what about the y? To get the y, we go back to the equation. The equation was 2x plus 3. So 2 times negative 6/5 plus 3. So you get negative 12/5 plus 3. Get a common denominator, negative 12/5 plus 15/5, which is 3/5. That's it. Now, I don't know how good I can draw this, but I'll zoom in on it. Okay, here's my picture. Here's the origin. That line went up 1, 2, 3. Here was the line. It had a y-intercept of 3. It went up 2 over 1, but I'm going to go down 2 over 1 this way and draw my line like this. The point that is closest to this one, this is negative 1. The point that's closest to this one is actually at negative, it's this point, negative 6/5, and then the y is 3/5. So if I go to negative 6/5, that's negative 1.2, and then up right here, somewhere around It's somewhere around here. Now this is a rough graph of it. I'm pretty convinced that that's it. That's the point that's closest to the origin. All right. So let's see, number... I think I might try and do some of the rest of these in class. Number 17 is close to what I did in class, and then it's kind of close to this one. Same concept. I think I might try and do 19, 23, and 25. Let me do 25. Yeah, 25 I think is a good one. I'll do 25, and then in class, I'll do number 19 in one of my classes, and I'll do number 23 in the other class. So number 25, this will be my last one. A Norman window has the shape of a rectangle surmounted by a semicircle. So this is a window that they put in buildings. It's called a Norman window. It's a rectangle, and then they put a semicircle on the top of it. So this is half of the circle, that's a rectangle. If the perimeter of this window is 30 feet, it says find the dimensions of the window so that the greatest possible amount of light can be admitted through the window. So I've got to make this window so it has 30 feet around it, but I want the most light coming through it, so I want to find the maximum area. The more area, the more light comes through. Find maximum, sorry, max area. So I need an area function. Need area function. All right, well, there's some things that could change in this problem that would affect the size of this Norman window. Let's call this distance from here to here. Let's call that x. And let's call the distance from here to here y. And if I have fixed this to be x, I know the diameter of this circle. If I know the diameter of the circle, then I know the radius. If I go from here to here, that's half of x, right? So I know the radius of that circle is half of x. I know the whole base of this rectangle is x. I know that the height of the rectangle is y. So the area of that should be the area of the rectangle, which is x times y, plus the area of this semicircle. So remember, the semicircle looks like this. The radius of this is half x. So the area of this little circle, we know the area of a full circle is pi r squared. So I'm going to take half of that because it's half a circle. So half of pi times the radius squared, but my radius is 1/2 x, right? Squared. So that's going to be 1/2 pi. When I square this, I get 1/4 x squared. And then putting all this together, I get 1/8 pi x squared. So I know the area of this, in terms of that picture, will be 1/8 pi x squared. That's it. That is an area equation. Unfortunately, it contains x and y in it. And I need it to just be in terms of one variable. So I'd like to get rid of that y. I have not used a constraint. So let's talk about the constraint. The perimeter has to be 30 feet. Well, what is the perimeter of this thing? The perimeter is, well, I've got to go x, right? I've got to go y, and I've got another y on this side. So it's x plus this y and this y, that's 2y. Plus, I've got to include the outer edge, the top edge of the semicircle. So I've got to include this, right? So what is the length of that? So back to this over here. This right here is half the circumference, right? Now the circumference of a circle is 2 pi r. So r in this case is half x. Okay, so do you see that? This is 2 pi r. 2 pi r is the circumference of a full circle. I want half of that. And so some 2's cancel here, and I just get 1/2 pi x. All right, so that's what I have here, 1/2 pi x. So that should be my perimeter, and that has to be 30. So let me just put 30 here instead. So the perimeter of the Norman window must be 30. I can solve this for y. It's not going to be pretty, but I can do it. So if I solve that for y, I get 30 minus x minus 1/2 pi x equals 2y. So that's just moving this term over and that term over. And I can divide by 2. So I get 15 minus 1/2 x. I'm dividing by 2, so minus 1/4 pi x equals y. There it is. So this is my constraint equation. And I'm going to take that and plug that in right there for that y. It's not going to look pretty, but I think it's going to work out nice. The area is now a function of x. It is equal to x times y, but y is all this. 15 minus 1/2 x minus 1/4 pi x. And then that's it. That's y. But then I still have plus 1/8 pi x squared. Let's distribute that x through. So 15x minus 1/2 x squared minus 1/4 pi x squared plus 1/8 pi x squared. And I do see that I have some like terms here. I do notice that I can put these together. I can also put that together, but let's try this right now. Separate this here. Okay, that's my work down there. Let's put these two together first. Same variable squared, and I can do negative 1/4 pi plus 1/8 pi. That should give me negative 1/8 pi. So I'm sitting here. I've got a of x is